And it's a real pleasure to have here for the colloquium of today, Alexandre Refregier, who is, as you know, a professor of observational cosmology at ETHZ. Alexander has started out in the US, actually, because he was a PhD student at Columbia. And then after getting a degree, the PhD degree from Columbia, he moved to postdoctoral positions in prestigious places, Princeton and Cambridge. Then after that, he came back to Europe and was a CNRS researcher at Secretary for a number of years. And then in 2011, he moved to Zurich at the ETH as a professor. And since then, he has stayed at ETH, and we welcome him today here. And so Alexander has worked on a very wide range of topics in cosmology, especially in connection with large-scale structure, lensing, and cosmological probes. He is a member of the most important collaborations working on observational cosmology probes like TESS and DESI. And he has a very large program also connecting machine learning and modern data science techniques to cosmology. As many people know, he's also one of the board members of SCATCH, where some of us are involved. So his interest is also towards the SKA and radio cosmology. And so with no further ado, I will leave in the stage. He will talk about Fourier modeling for cosmology.
Okay, thank you very much, Lucio, for the introduction and invitation. It's a real pleasure to be here and see you again, see old faces, and also meet new people as well. So today I'll be talking about this forward modeling approach in cosmology for several reasons. So first, it's advancing quite quickly as a new approach to analyze data and interpret data in cosmology. And also, I was thinking that since you have a very strong effort and expertise in computational astrophysics, then I hope this would be of special interest to all of you. And a lot of the work I'll be describing has been done with the junior people who are listed here, and also with Aurel and Joachim for the simulations particular effort that is crucial to this research program here. So cosmology is a field that has made impressive progress in the last few decades. And now we have a standard model of cosmology called the lambda CDM model, which has been established through very impressive progress in telescopes and instruments, and also in computational science as well. And we now have quite a good picture of the history and evolution of our universe from the very early times after the Big Bang until today, going through important phases which are driven by the expansion and cooling down of the universe in our Big Bang paradigm. So we now know we can describe the physics of some of these different phases, and also the physics in particular of the formation of structures that led to the universe that we see today, with all the structure that we see on all scales, going from planets, stars, galaxies, cluster of galaxies, and so on. However, there's of course many open questions that have appeared during the establishment of this model. The two of the important questions have to do with this dark component of the universe, dark matter and dark energy, which together make up about 95% of the energy of the density of the universe, and whose nature is unknown. So matter, dark matter, drives the formation of structures. It dominates the matter density in the universe, and dark energy is an even more mysterious component that drives an acceleration of the expansion of the universe at relatively late times. Related to this, perhaps, is the nature of gravity. So one of the questions is whether our theory of gravity, which is Einstein's theory of general relativity, is valid on these very, very large cosmological scales in a weak field regime. And perhaps some of these components which manifest through gravitational effects are related to potential modification of gravity. There's also a very interesting question having to do with the initial condition and a phase we call inflation to generate the conditions in a very early universe, solve a number of problems, including the origin of the seed of structures. Now, in order to make further progress with this, and in order to establish this model, the way we do it in observational cosmology is to combine different cosmological probes, right? And we combine different cosmological probes, which are sort of different windows that we have on the universe that allows us to get complementary information on our universe. So it gives us complementary information both at different epochs, but also through different physical processes that we can combine together to get the full picture and eventually lead to the establishment of this concordance model and potentially extensions of it or modifications of it. Now, these cosmological probes are combined both to get more information. So each of these only give a limited information. There's so-called degeneracy, so correlations in the posterior of the different cosmological parameters that we want to constrain. And also, very importantly, it allows us to control systematic effects. Each of these have their own systematic effects. Some of these systematic effects are experimental. Some of them are astrophysical. And by combining them, we can cross-check the systematic effects, check that they're not dominant, and also reduce, therefore, the size of the total error bars, which include the statistical errors. Now, one can maybe distinguish or classify these different cosmological probes into 4 classes, as I've done here. So the first one is the cosmic microwave background, which gives us a picture of the universe at relatively early time, when the universe was about a few 100,000 years old. It gives us the conditions and the picture of the state of the perturbations and their statistics at that time. And until now, it has been the probe that has given the most amount of information. Another way to say that is the one that has given the smallest errors on our cosmological parameters. And it has been remarkably successful over many decades now, and we have exquisite measurement of these cosmic microwave background temperature fluctuations that we can measure. Another class of probes is what I wrote here as geometrical probes, or sometimes they call standard candles, standard rulers, standard sirens. So these are probes that allows us to have a standard distance of some kind or another, or a standard luminosity, that gives us a scale that we can measure as a function of redshift or as a function of time, and from that learn about the history of the expansion of the universe. So this measures the information about the background expansion, not about the perturbations, and that also has made remarkable progress, and we now have even gravitational waves that give us also one of these standard scales. Another example, of course, is supernovae. Another one is, for example, baryon acoustic oscillations. And these are very important because they give us perhaps a more direct measurement of the background expansion and can be compared to some of the other probes. And then we have the probes that give us information about the structure formations in the more local universe at relatively late time or relatively low redshifts, and they can be classified in 2 categories. So the first one would be what I would call clustering, and by that I mean clustering of visible matter of one kind or another. The typical one is the clustering of galaxies. So using large galaxy surveys, one can measure the 3-dimensional distribution of galaxies. One can also use clusters of galaxies. We can do it in X-rays, in optical, in most of the wavelengths, in the radio as well. And these tend to give us a very high signal-to-noise measurement of the distribution of this visible matter. And from that, we can infer cosmological parameters by using our theory of cosmological structure formation and the fact that the statistics and the evolution of these structures depend on the value of our cosmological parameter, in particular on the components that fill the universe. Now, one of the difficulties in this approach with the clustering of visible matter is that one needs to make assumptions about the relation between the distribution of visible matter and the distribution of the dark matter. The dark matter drives the structure formation, so it's the component of matter that's the most important and can be most easily compared to our predictions for structure formation. And one has to make an assumption about the relationship between the visible matter and the dark matter. Now, we have very good reason to believe that on large scale, we can use a relatively simple bias formalism in order to do this. On small scales, it's much more complicated. And this is related to the fact that the theory of galaxy formation is very complicated and is not a fully solved problem. Now, one way to give complementary information to get around this is to use gravitational lensing. So gravitational lensing uses the fact that photons, when they propagate through an inhomogeneous space-time, leads to various distortions in the images of background objects. This was actually already observed or noticed by Einstein early on when he developed his theory of general relativity. And using that, we can statistically reconstruct the distribution of the density field in the universe also as a function of redshift, and therefore directly probe the dark matter, which, as I said, dominates the density perturbations. Now, the price we pay for this is that gravitational lensing is a much harder measurement. The effects that are generated by weak lensing are very small. So one needs to correct a number of instrumental effects, also a number of astrophysical effects. So it's quite a difficult measurement. And it's also typically a much more noisy measurement. So I would say gravitational lensing is easier to interpret as some of cleaner physics, but on the other hand, the signal to noise tends to be much lower. And that's why typically these two probes, the clustering visible matter and gravitational lensing, are complementary and often, as I'll show later, combined together to get around the challenges in either method taken separately. Now, this is very exciting, and we now have many experiments that are designed to make measurements with some of these these different cosmological probes. They're called wide field instrument because in order to make the measurement and have a small statistical error, we need to probe very large volumes. And therefore, we prefer to have instruments that have a very wide field of view so that we can map a very large part of the sky and therefore get much larger volumes in the universe. So there's the cosmic microwave background experiments. So the latest space telescope, which is Planck, is now has given its final results. There's ground-based experiments being developed and new generation of CMB experiments that are under construction. In the visible near infrared, which is where until now most of our this is the range where most of our galaxy surveys are being done. Have a combination of imaging and spectroscopic. So some experiments are purely imaging, some experiments are purely spectroscopic, and also some of them have both, right? And so there's a number of experiments. There's what we call stage 3 experiments, which are the experiments happening right now, and then the stage 4 experiment, which is now getting online, which will soon give us some of them already started, and soon we'll have much more information. So the current experiment are, for example, KIDS, DESI, Subaru, and so on, and the next generation will be Euclid, Subaru, and also LSST as well. There's also a very exciting new area for these kind of cosmological measurements, and that's in the radio domain. As Lucio described before, the largest experiment under development is the SKA, which will be a very large array of telescopes in South Africa and Australia that can give us amazing measurements of various probes in cosmology. And there's also precursor experiments which are being built now. And if there's time at the end, I'll say a few words about one of these experiments. Now we are at this time in observational cosmology, we're kind of in a transitional time. So as I said before, until now, it's the CMB that was driving the constraints and the information content of our cosmological measurements. And it took several decades for the community to learn how to analyze CMB data. So these are difficult analysis. These are what we call high precision cosmology. So it requires new techniques, new simulation techniques, as well as new data analysis techniques. And now that's very established and very mature, still very difficult, but there's a lot of techniques to do this. And this was mainly these techniques were developed in the context of the format of the CMB data, which is, if I simplify a little bit, basically working on a sphere. So the data is mostly a map on a sphere. In reality, there's actually a couple of maps, but I'll simplify for the moment. So it's map on a sphere from one experiment, and the field that we're mostly interested in, which is the primordial fluctuation, the temperature of the CMB, is Gaussian, mostly Gaussian. So we have a Gaussian field on a sphere, whose statistics needs to be measured with very high precision. And now we have very good techniques to do this. Okay. But now we're transitioning, especially when we now have from the stage 3 to the stage 4 galaxy survey experiments. We're transitioning to the time where the galaxy surveys or the large-scale structure surveys in general will start to have comparable precisions compared to the cosmic microwave background. And so what we need to do now is to learn how to obtain the same level of precision and accuracy not only for the cosmic microwave background, but also for the galaxy surveys. And that's much more challenging for various reasons. So first of all, the galaxy surveys are intrinsically three-dimensional. So it's also spherical geometry, right? So we have the surveys are wide enough that we need to take into account the curvature of the sky, but it's also three-dimensional because we have radial information. Another reason is because we typically have to combine different experiments together, while the CMB was, again, I'm simplifying a little bit, but mostly driven by a given experiment. Here, we typically have to combine different experiments, for example, an imaging survey and a spectroscopic survey, for example. That adds complexity to all the measurement and the calibrations. Another reason is that the fields that we're probing, the data, the statistics we're probing are intrinsically non-Gaussian and non-linear. They're non-Gaussian because they come from small scales, for which non-linear evolution of structures have played a role. So we can no longer assume that the quantities that we're dealing with have Gaussian distribution. So we need to also capture and deal with the non-Gaussian nature of the data. And their systematics limited. I would argue that the CMB is also systematics limited, but here the systematics are perhaps more complex and more varied than the CMB. And the data volumes are much, much larger. Typical CMB experiments have resolution of the order of an arc-minute, while, let's say, an imaging galaxy surveys has resolution of sub-arc seconds. And therefore, the amount of data that needs to be handled and modeled and corrected is much larger. So now the challenge is to be able to attain the same precision with these challenges. And there's a lot now of development and progress in making that transition. And one of these approaches is the forward modeling approach, which I was telling you about before. I think you can interrupt me at any time, right? All right, so let's start with an example. So I'm going to progress into different level of analyses, one from a more standard analysis, doesn't mean it's easy, and you'll see it's very difficult, to more and more recent approaches to the data analysis of some of these galaxy survey. Now, in order to do this, I'm going to use, okay. Let me see if that works. Yes, okay. So in order to do this, I'm going to use one example, which is an experiment that we're involved in. It's called the Dark Energy Survey. So it's a wide field camera that you can see on the right, which was mounted on this telescope that you can see on the mountain here on the left. It's the Blanco telescope at CTIO in Chile. And at the time, the camera you see on the right, you see each rectangle corresponding to one CCD. Each of them is a 2,000 by 4,000 CCD, was the largest, the most powerful astronomical camera which had been built at the time. And this allowed this experiment to map a very large sky area with good image quality in five bands, okay? And the ultimate survey area is about 5,000 square degrees. And in one image, one covers a field of view of 2 square degrees, okay? So it allows us to go both relatively, get a very wide area, but also quite deep, given the telescope, the 4-meter telescope that we have available. And that gives us a catalog of about 200 million galaxies for cosmology, which is quite impressive. Now, one of the driving cosmological probe for this experiment is the gravitational lensing. And the idea here is to take these images generated, observed with this telescope, analyze the shape of galaxies. From the correlation, the shape of galaxies, we can reconstruct the intervening dark matter or density perturbations. And then we can first make a map of the distribution of dark matter in the universe. And here is the latest map from this experiment. It covers about 4,000 square degree. So you see the region, the survey area of the survey projected on the sky. The brightest regions correspond to overdensities, and the darker region correspond to underdensities, as you can see here on this color bar. All right, and you can see now these patterns that one can study statistically in order to compare to predictions and constrain our cosmological model. Now, there's different ways of doing it. So the first one is to use the lowest order information available to capture the clustering of this dark matter, and this is using the 2-point correlation function that you see here. So it's quite a busy plot, but each of these panel shows you a measurement of the so-called 2-point function that tells us how much clustering there is in the dark matter, or in the density more precisely, as a function of angular scale. Okay, so you see the angular scale here in arc minutes, and this gives the amplitude of the perturbations of the density field projected onto the map. Now, the reason we have different quadrants is because, first of all, what we measure is a vector quantity. So we have several correlation functions that we can consider. It turns out there's two that are important. So there's one on the upper left and another one on the lower right. And inside each of these triangle, you see there's many plots. And the reason is because we do it not only for one map, like I showed here, but what we do is we do what we call tomography. So we take our galaxy catalog separated in different redshift bins. And then we can make basically several maps corresponding to several redshifts, or corresponding to several distances, if you wish, and therefore get also radial information for the measurement. So here you see the distribution in redshift of these 4 redshift bins. So using color cuts, one can separate the galaxies into these different bins. You see there's a low redshift bin, mediums, second medium, and then high redshift. And we can measure the correlation function for each of these bins. That's what you see on the diagonals, like the label 1, 1, 2, 2, 3, 3, and 4, 4, for example. But we can also measure the cross correlation between the different bins that gives us even more radial information. That's what you see on the off diagonal, like 1, 2, 2, 3, and so on. Okay, so it's quite a complicated measurement, but we can measure all of that as a function of scale, as a function of the bin, and then we can compare that to a prediction. So if you look at the green line, this is a prediction for these statistics coming from models of structural formation. This is the best fit that was adjusted to fit this data. This is a 6-parameter fit corresponding to our different cosmological model. In addition to that, there was also a number of systematic parameters that are marginalized over. And in this case, we can use our understanding of structural formation to make analytical prediction for this correlation function and fit it to the data. Now, in reality, it's not quite analytical. There's still numerical integrations of various integrals. There's also, in the nonlinear regime, numerical fit to numerical simulations to give us the correction for nonlinear evolution. But that, when all of that is done, we can have a relatively quick evaluation of a prediction for the statistics for any value of a cosmological parameter. Yeah, Jayu. All these little lines, yeah, these corresponds to, so yeah, the different lines. The one to look at are the sort of black lines in the middle. The other one corresponds to different realization, which characterize the error in the estimation of the redshift distribution, right? So there's an uncertainty in the redshift distribution, and this gives you an ensemble corresponding to the, gives you a sampling of the error of these distributions. So in reality, we don't know this. So in order to predict this correlation function, we need to assume a redshift distribution, but there's an uncertainty in it, and so we marginalize over the uncertainty. We can measure it, but there's a, so we use to measure the redshift of the galaxies, we use photometric redshift. So we use colors as opposed to an emission line in a spectrum, which would be way too expensive observationally. So we get only an approximate measurement of the redshift. And therefore, we are left with an uncertainty. It's because there's an uncertainty in the calibration of the photometric redshift. So not only there's an uncertainty per galaxy, but there's an uncertainty in the overall redshift distribution because we have an uncertainty in the calibration of the photometric redshift. In other words, on the relation between the colors and the redshifts. No, we use this actual estimation and we marginalize over that uncertainty. Yeah, that's actually a very difficult aspect. Perhaps now one of the dominant systematic error, which is the uncertainty on these redshift distributions. Yeah, yeah, please. Yes. So it's never too much, right? In terms of so if we can have a larger area, that would be even better. And so you see the size, so these are the measurement in black, and you see the size of the error bars. A large contribution to the size of these error bars is the finite area that we have, or the finite number of pairs of galaxies that we can use. So the area that we have will determine the precision that we get on this data. That's why we want more and more and more area. The next generation will get even more. So if you focus on the smaller region, we would get another measurement with larger error bars. So if let's say you split it into two, you would get two measurements with larger error bar. Hopefully they will be compatible. So there are lots of checks done. I mean, I'm joking, but there's lots of checks done on doing different areas. For example, the galactic latitude is very important because, of course, the galaxy has different properties if we look in the plane or out of the plane. For example, the number density of stars that we don't want for our measurement increases, so it makes it more difficult. So we check that the signal, that many checks that the signal is robust to cuts like this. Yep. Yeah, many checks. It's a very difficult measurement. There's a lot of checks on the shape measurement of galaxies, on their redshift, on possible variation across the field, all sorts of check on variation of the observing condition, like the seeing, for example. Many checks go into this. Yeah. Okay. So once we've done that, we fit these predictions, these semi-analytic predictions, to the simulations. The predictions can be done relatively quickly. We can vary our parameters, get a fit, and then we get constraint on our parameters. Okay. Now this is the constraint that we get on two parameters, which are the ones we constrain from which we get the strongest constraint. So what is plotted is constraint on omega m that you see on the x-axis, and sigma 8 that we plot on the y-axis. So what is omega m sigma 8? Omega m is basically the amount of matter in the universe. Now it makes sense that we are sensitive to that because if there was no matter, we get no lensing. So we get 0. The more matter do we have, the more fluctuation we can detect. Another important parameter is sigma 8 that characterizes the amplitude of the fluctuations, right? And after all, this is what we're measuring with lensing. We're measuring perturbations. If we have matter but it was homogeneously distributed, we get no lensing, so we need perturbations. So it makes sense that what we measure very well is the amplitude of the perturbations. So this is the RMS of the perturbation, smooth on an 8 megaparsec sphere. Now you notice that the constraint we get, and I'll come to the different colors of the many lines here, are degenerate, right? See that the degeneracy between sigma 8 and omega matter. And that's why sometimes we take a combination of sigma 8 and omega matter. We form what we call the parameter S8, which is just sigma 8 times omega to some power, to flatten this the contours. You can see it on the right, and characterize more the actual amplitude, the general amplitude that we measure. So I'll be going back and forth between sigma 8 and S8. They give the same information, but just different parameterization, which are sometimes convenient. So if we go, for example, in the S8 as an example, you see the constraint from this DS Y3. So this is from the UR3 data release that you see in this sort of pale blue and green contours. And you see also measurement from other similar weak lensing analysis with other experiment. One of them is particularly the kids survey here that you see in sort of these dark blue contours, which are consistent, but perhaps a little bit lower, but not perhaps a little bit lower. And there's another experiment called the Subaru telescope HSC, which also gives the contours either in red, which tend to be higher. And then, very interestingly, is that we can look at the yellow contours. So the yellow contours are the constraint derived from the cosmic microwave background measurement with the Planck satellite. The Planck satellite does not directly measure this parameter because this corresponds to the amplitude fluctuation locally. But you can, given the other cosmological parameter, you can extrapolate from the amplitude of the fluctuation at very high redshift to the one that we see today. And so you can also project the constraints of the Planck satellite onto this plane as well. And you see that these yellow contours tends to be in a different direction, but also higher. And this is what we call the sigma 8 tension or the SA tension. There's a small tension, about 2 sigma, between the measurement of the Planck satellite at high redshift and the lower redshift measurement in this weak lensing measurement. You also notice what I said before, we have these degeneracies for a given probe, but they tend to be in different directions. The Planck, for example, is more vertical, this is more horizontal. So when we combine them together, of course, we get stronger constraints. Now, in order to combine them, however, we should not have a tension, because if we have a tension, there's something missing, either a systematic effect in our analysis or one of the analyses or both, or the model that we're fitting needs to be extended. We need to put more physics to fit the data simultaneously. Of course, if it's new physics, that would be the most exciting. However, usually it's systematic effects, but I'm an observer, so I'm more careful. But theorists have written many papers to explain this. Okay. Now, what we can also do is, given this the dark energy survey, it gives us a measurement of lensing, but it can also give us a measurement of the position of galaxies. And after all, for lensing, we're using galaxies, so we can also measure their clustering. So we can combine the weak lensing and the clustering. So again, if we look, for example, at the sigma 8 omega m plane, the lensing one that I was telling you about is the black one, right, with different level of confidence, either the dashed or the solid, the contours here. And then, the weak lensing only, is the blue one that I was showing you before. If we add now clustering and also the cross correlation between clustering and lensing, we get the orange one. And now if we combine everything together, the lensing and the clustering and the cross correlation between lensing and clustering, then we get the black ones, okay, which are smaller and therefore give us higher precision, okay? And also with this, we can also measure other astrophysical parameters like the galaxy bias and so on, and other parameters intrinsic to the lensing measurement, which are also very interesting. Now we can compare that to the, again, the Planck analysis. So if we look here on the top here, S8 versus omega m again, this, the black contours corresponding to the dark energy survey lensing plus clustering. The green is the Planck. And then if we combine them together, even though there's a small tension, we get the orange. Now, this is an example. So first of all, there's always this question of the tension. But interestingly, also, what you can see is that these sort of gray contours, the size of these gray contours, are starting to be comparable with the green contours. This is what I was telling you. The galaxy surveys are starting to have constraints which are comparable to the cosmic microwave background constraint, at least in some parameter space with some assumptions. We're not quite there yet. But when we get to the stage 4 measurement, we'll get even closer. That's what I was saying. The information content of these galaxy surveys is starting to be comparable. By the way, we can also constrain the dark energy, and we find results compatible with a cosmological constant. Okay, now this is what I would say a standard analysis where we measure a summary statistics. In this case, it's the correlation function. We can make a prediction for this summary statistic using our theory of structural formation. We can fit the two together, get constraints. Now, it's standard doesn't mean it's easy, it doesn't mean it's not important. It's just that this is the standard approach we've been using in science, in physics for many years. However, we can try something more ambitious. And in particular, we might be interested in capturing higher order information in these statistics. As I told you, the field that we are probing using these galaxy surveys are non-Gaussian. So it means there's information beyond this correlation function, beyond the 2-point function. I can here on the left, what you can see is it's not coming out very nicely, but it's okay. You can see a numerical simulation showing a simulated dark matter map or density projection map for weak lensing. And you see that this map has a lot of clumps, very, very clumpy regions. And these clumpy regions are nothing other than galaxy clusters and galaxy groups that, due to nonlinear evolution of structure that you can sort of see on the top, collapse through nonlinear evolution and give very, very dense region. So this field has a lot of, as a special texture. You also see a remnant of maybe of filaments and so on. So the field has a special texture, which is a signature of the formation of a structure formation process in the nonlinear regime. And we would like to be able to characterize that statistically, capture this information, and from that get stronger constraints from our weak lensing measurements, and also check what we whether it agrees with what we predict, what we get from the 2-point function only. Okay, now how do we do this? So that's an unsolved problem. How do we capture all the non-Gaussian information in these non-Gaussian maps? And there are many techniques that have been. Did you have a question? Oh, no. There are many techniques that have been developed in order to do this. There's higher order correlation function. We can look at a 3-point, 4-point function. We can look at all sorts of geometrical statistics. It turns out there's one statistic which is actually very powerful and simple, and that is called peak statistics. And we did many studies in the past, and we saw that the peak statistics, even though it's simple, it's one of the higher performance. It performs very well. And this is and physically comes from the fact that, as I said, the texture of these maps is mainly these peaks. So if you can measure the property of the peaks, you capture a lot of the non-Gaussian information. Not all of it, probably, but a lot of it. So that's what we did. So we have one student here in our group, Dominic Zürcher, who did a peak analysis of this dark energy survey year 3 release. So basically what he did is that he took the map that I showed you before, and then what we can do is we can identify the peaks, so the yellowest region, and he counted the number of peaks as a function of the strength of the peak. And he can do it again for each of the maps or each of the redshift bins. He can also do it by multiplying the 2 maps, by also doing by cross-correlating two redshift bins as well. Okay, and you can see the measurement here. So again, we get this kind of matrix of summary statistics. So on the diagonal, you see the measurement for bin 1, bin 2, bin 3, bin 4, and then off diagonal, you see the cross correlation between bins. And then the data point is focused on the data points for the moment, the black points with the error bars. This corresponds to the measurement, and what it is the number of peaks as a function of the amplitude of the peaks. It's been divided, but what has been subtracted here is the number of peaks we expect from noise alone. So the maps are noisy. Even with noise, we get peaks. So we subtract that, and we get this characteristic curves. Now, once we have this measurement, we can ask, well, how do we get cosmological constraint from it? Now, the problem is that for this particular statistics, and that's the case for many of the non-Gaussian statistics, we don't have a way of predicting robustly, analytically, the peak statistics for different values of cosmological parameters, because the detection of the peaks depend too much on the detail of what we mean by a peak, right? So it depends on the noise level. It depends what we mean. Do we mean maximum? Do we mean a threshold? So it's too ambiguous to obtain a prediction of the summary statistics which correspond to the actual peaks that we're measuring. Okay, so So we run a peak finding algorithms, and what we do is actually wavelet filtering, and then we look for maxima. And we do it at different, so it's a bit more complicated. We do it also at different scales. So we measure peaks after smoothing on different scales, so peaks of different sizes, and we combine all of that together. Yeah, exactly. Yeah. Convergence map. Yeah. Is the redshift bin. Is the redshift bin, right? So on the diagonal, you have the first redshift bin, second, third, and fourth. And the off diagonal is the we multiply the two maps from the different bins, and then we look for peaks in the combined maps. So it gives us a bit more radial information, just like we did for the 2-point function. Yeah. In this case, he only did 4 bins. Yeah. Did we have 5 bins before? No, we also had 4. We also had 4. Too much, yeah, too much systematic, yeah. Yeah, there was one, but so actually the higher the redshift, the more information the bin has, because the lensing amplitude happens to be larger. But on the other hand, the harder it is to measure, because the galaxies are fainter, smaller. The photometric redshifts are even harder to calibrate. So there's more information, but it's harder. So we make cuts where we don't believe the data anymore. Just like, by the way, we also make cuts in scale. I mean, I didn't highlight this before, but these bluish purple areas are areas that we reject. Actually, on small scale, we reject a lot of the data because of systematic effect, or we don't know how to interpret it due to various astrophysical effects as well. So we make a lot of cuts to define the region of the area of the region of the data that we can trust. Okay, so when we do this, so in order to do this, so we cannot get analytical predictions, so we have to use simulations. That's where this forward modeling comes in. So what we do is, as an example here, we forward simulate the data. So we take a cosmological parameter, we then run an n-body simulation. In fact, we use the PKD graph simulation that you all know here very well, of course. And then we generate weak lensing maps from it. We add all the instrumental effects, so the noise, the point spread function, some of the astrophysical effect like intrinsic alignment, and so on. And then we generate a simulated map in exactly the same format as the real data. And then we apply the exact same algorithm for finding the peaks to the simulation, then we do to the data, and then we get predictions. So this colored line corresponds to predictions, in this case, for different value of this S8 parameter, for example. And of course, you see that the amplitude of this peak statistic depends very strongly on S8, which is not surprising. The higher the S8, the more peaks you expect. Okay, so that's another, it's a next level of analysis, you see, where we can't predict we have a summary statistics. We can't predict it analytically, but we can predict it using simulations. So we do a simulation-based analysis, basically, for the prediction of the statistics. And of course, it requires an enormous amount of simulations to probe all we need to scan all the cosmological parameters and have many realizations to get good statistics on our simulations. And also we need to put in a lot of physical effects so that the simulations agree with the data statistically. And that's what was done. And that's what Dominic found. So again, if we look at the omega m S8 plane, we see what we would get from the correlation function alone. We do this, actually, it's in Fourier space, so it's a spherical power spectrum, but it's the same information. So in blue, that's the 2-point function alone. In orange, the peaks alone. And then if we combine both, we get the green contours. And you see that the peaks add more information and allows us to get much stronger constraints on the S8 omega m. We can compare to Planck, for example. So this is our peak plus 2-point function. This is Planck, and this is the kids survey with the 2-point function alone. Now here for this analysis, we were due to technical and also physical limits in systematics, we're quite conservative in the scale that we used in order not to over-interpret the data and also be able to run these simulations. So our controls are still relatively large compared to the 2-point function analysis that was done before. But nevertheless, it's still very interesting to compare the two and get this additional information. So this, basically, if you think about it, the comparison between the blue and the green is the reduction of the errors coming from the green is what we gain by capturing some of the non-Gaussian information. Okay. How much time do I have? 5 minutes? 10? Yeah, perfect. All right, so now let's try to get to the next level. All right, so what we did until now, just to repeat, we have our observed weak lensing map. We have a summary statistic that somebody has invented, 2-point function, peaks, okay? We can plot it, so this would be the white error bars. And then we have a theorist that can make a prediction for it. If it's the first case, we get a analytical prediction. If it's the second case, we have to use simulations. And then from that, we do a fit, and we obtain cosmological constraints, okay? Now, can we go even further and use machine learning, all right? So instead of using a summary statistic that a human has invented using their physical intuition, can we get a machine learning algorithm to do it, to learn the statistics? So the idea is the following. What we can do is we can generate a large suite of simulations that we anyway need for the second case, right? And we can, for these simulations, we can label them by the true cosmological parameter. So we sigma 8 is 0.8, give it to the machine with that map has sigma 8 of 0.8, this map has sigma 8 of 0.7, and so on. We give them thousands and thousands of simulations, and the machine learns the relation between the map and the cosmological parameter without telling it to measure something, okay? And for that, we use deep convolution neural networks, train it on a very large suite of simulations, and then ask it what constraint we get. Now, by the way, we can debate the philosophy of that. I'm sure we will. But we do all of this blinded anyway, even for the human statistics. So we don't look at the final result. We don't look at we only look at the final result at the end. We don't look at the final result and then change our analysis until we get something that we like. We have various tests to decide whether we're ready to unblind. And then once we're ready to unblind, we unblind, and it's whatever it is, okay? We want to avoid the human biases having to do with confirmation bias, basically, especially at this very high precision that we're working on. That's used now more and more in cosmology. So the machine learning is also blinded. I mean, of course, the machine itself doesn't care about what the result is, but it's not like we redo it again until we get a result that we like. And here is the first implementation of this. That's another PhD student, Yanis Fleury, who did this analysis. So he did it on another survey called the Kids 450 survey, which is a similar survey to DS, a little bit smaller at the time. And what you see again, sigma 8 omega m, sorry, it's always the same the same plot, but this is easier to compare. You see the constraint on the sigma 8 omega m using the power spectrum alone, so only the 2-point function, that's in green, okay? And then using the machine learning, that's in blue. And you notice, I mean, it's quite amazing that the machine, so first of all, they agree. So the green one is a human made statistics, only capture Gaussian information. They agree, but also the machine learning tools are smaller. So it means that the machine has managed to not only agree with the 2-point function measurement, but it has managed to also capture non-Gaussian information and therefore get stronger constraints than the 2-point function. So that was quite a we're very happy, again, blinded. We can also compare to earlier measurement with Planck. And here again, we're a little bit, so this is, the Planck is in green, this is ours. We're also a little bit higher than the earlier measurements. We tend, our measurement tend to always be a little bit higher. So our tension is smaller, but it's not very significant, but it's still interesting to see. Now, this was done in a relatively simplified, not condition, but simplified analysis where we did not vary all the cosmological parameters that the standard analysis has been using. So it was a simplified analysis compared to the human analysis that had been done before. So Yanis then went on and did an even more advanced analysis where he did a full analysis. This time it's comparable in terms of treatment of systematics, number of cosmological parameters that was varied, and so on. And he did it on a larger data set, which is a Kids 1000 data release, which is the one that came after the KISS 450. And you can see the contours here, again, omega m sigma 8. So the 2-point function, the power spectrum, is in black. It's hard to see. The blue, the dark blue, is the machine learning constraint, and the green below that you see here is the standard KISS 1000 analysis. In this case, he also used an extension of the standard model where we varied the dark energy equation of state W, so it has an extra parameter. We can see the constraint of the dark energy equation of state as well. Now you see here that he has a slightly, the machine learning is slightly better than the power spectrum, but not by a big margin. And it's also compatible with the KISS 1000 official analysis. The reason the performance of the machine learning, while it's still good, doesn't, I mean, it still agrees with all of this and the 2-point function. It doesn't improve as much as it did here. And the reason is that, again, for technical reasons, we could not include very small scales in the analysis because of the amount of simulation necessary and the resolution needed. So we are constrained to slightly larger scales, which means that we didn't have as much information. In particular, we didn't have as much non-Gaussian information. But nevertheless, it showed that it works, that the machine learning can capture the information available, does as well as humans, even in the full analysis that we want to do. Now, in order to do this, we need large suites of simulations. So I'll say a few words about this. This is a large effort also with that we did with Aurel here, which is the Cosmo grid, and Joachim as well. So what is it? What you see here is an example of some of these simulations we run. These are a public set of simulation. Until recently, I think it's one of the largest one that was done for this purpose. You see the cosmological parameters that are varied. Each point is one value of cosmological parameter that we consider. We have 2,500 unique cosmologies. We have 7 unique initial conditions per cosmology. We also have a fiducial value here where we have much larger number of simulations, about 200, to get more statistics for one cosmology. And then this is the basis of this forward model analysis. And in here, we've added Aurel's baryonification model, which add the effect of the baryons and many other effects as well. So if you're interested, you can use them and download them and do forward model analysis like this, or even machine learning. Another interesting software that we do in order to do this is that we need to go from this n-body simulation, so the distribution of dark matter in 3 dimensions, to the observables. In this case, for example, the weak lensing, and this is done with another software that we call UFalcon ultra-fast light cone generator that goes from the n-body to maps, basically, or to at least light cones and shells. You see an example of a weak lensing measurement. We test the statistics of these simulations with analytical prediction when they can be done, and we can simulate this way the weak lensing maps. And now, more recently, we have another student, Alexander Reeves, who's now extended this. Well, Raphael here and Alexander Reeves, who's extended this to the different probes. So not only the weak lensing that you see here, but also to galaxy clustering with some simple assumption for the moment. Also for CMB lensing, the lensing effect on the cosmic microwave background, and also one of the component of the cosmic microwave background called the ISW effect. So for every cosmology, we realize it, and then we can generate self-consistent maps of all the different probes in such a way that we can also analyze all the other probes simultaneously at map level using this technique. And this is an example of a forecast that Alexander Reeves did. You see, so this is not a measurement, this is a forecast. This is using a 12 2-point function, right? So it has the autocorrelation of each of these and the cross correlation between them. Some of them are tomographic, so there's many power spectra for each, or many maps in each of these, for example, in these 2. So there's many maps, and there's the measurement of all the correlation function and the autocorrelation function and all the cross correlation. This is what we call a 12 cross 2-point analysis. And you see the constraint. If we use only some of the probes, and then if you use the full all the probes together in one go. And you see the stronger and stronger constraint that we get. One of the targets we're trying to get to is the mass of the neutrino. You see that you get a better constraint on the mass of the neutrino, which is a very hard, difficult measurement to do. Alexander also showed that he gets much more robust control of systematics due to a sort of self-calibration of the different probes that probe the large-scale structure in different ways, so we can auto-calibrate all these probes simultaneously. I think I'm out of time. I'll just say that if you're interested, I can tell you about this very exciting radio experiment that for which we use the forward model approach as well in South Africa. Very excited about this in the desert. Please come see me. And I will stop here. Thank you very much.
Couple of questions, one more general, one more technical. So the more general is when you go to field level analysis, you try to gain more information, especially from non-Gaussianity, right, small scale. So you have So you have two different challenges. I would say one is technical. You have to run a lot of simulations at a very high resolution, and that with computations we can maybe go beyond that. But the other is also theoretical, because we have to trust our model.
That's right.
To those scales and to higher order. And that's, I think, even a more concerning challenge, right? Because we can maybe trust our models to do well with baryonic effects, with nonlinearities into point, but then it's not given that those models are correct at field level. So,
I completely agree. So I completely agree. So one needs to be very careful not to overinterpret the data in a regime where our theoretical model is not accurate. But I'll come back to that. But I would say one thing is that even at the 2-point level, okay, even if we forget the non-Gaussianity, this map level analysis with the forward model is very interesting. The reason is that the analysis steps are very complicated. There are many nonlinear steps, actually. And by doing this forward model, we can, instead of doing an inverse problem, we can forward model without doing an inversion and still get, I would argue, we can get better treatment of systematics, and we can test the systematics much more carefully because we don't have to worry about this inverse problem or predictions of a systematic. We put it in, fold it through the entire instrument analysis simulation, and then so I think even at the 2-point level, even on Gaussian scales, it's still very useful. In fact, the CMB, they do it all the time, right? The CMB, even is Gaussian on a sphere, they do this forward simulation all the time. That's how they validate the result. Now, if you want to extract all the information, we have to be very careful, and we need to test. Indeed, there's prescription that we have, which we've validated more or less at the 2-point level, but they're not necessarily okay at field level. So we tend to be very conservative with our scale cuts. And I think, to me, the more promising approach is this probe combination. So the idea is that instead of trying to get everything out of weak lensing, where we push, because we only have weak lensing, so we push our model, our baryons, our intrinsic alignment to the maximum, we're going to small scales because we want to make the best measurement. We're more conservative in each, but we combine them all at field level. And then we get the cross correlation and all the validation coming from the cross correlation. So that's why I think it's actually probe combination, which is the approach. And then once you've done that, you can try to refine each of them. But I would go first horizontal and then deep. Yeah, to address exactly this. Yeah.
What kind of new physics would this thing?
Ah, that's very good. You're saying we reduce the error bars by 1 order of magnitude or something like this. Very good. Okay, that's a question we often get. I really like this question because it's very legitimate. So, why do we need? I mean, we know already at the percent level, omega m. I mean, look at it. I mean, it's pretty amazing. 5% level. Why do we need even smaller error bars, right? So the reason is because if we go back to our cosmological model, which fits the data very well, up to some tensions when we worry about, but let's ignore that for the moment, fits very well all of these observations. Great, why do we, fine, and why do we need to know it even better, right? So the reason is because, at least in my view, that's a philosophical question, but in my view is because if we look at a cosmological model, there are certain sort of ingredients in the model that are very well founded, like general relativity, for example, gravity, evolutional structures, but there are many ingredients that have been put by hand to fit the data, okay? So we first had only ordinary matter and gravity. That didn't fit the data. We made measurement of the cosmic microwave background and fit the data. We had also observation low redshift. We added dark matter to fit the data, okay? Then we had even better measurement at late time of the expansion history, didn't fit the data. We added dark energy. We don't know how to generate our initial conditions, so we invoke a phase in the early universe called inflation that generates initial conditions, solve all the problems, but it doesn't come from a fundamental, it doesn't come from the Lagrangian of the standard model of particle physics. It's put by hand. The potential is also tailored. Maybe our theories disagree, but we can see. But I mean, you tailor it so it fits. So to me, it's a model that fits the data very well, but we have many ingredients that we don't understand, like don't understand at all. Some of them we can think it's fine, but others we don't understand at all. So the goal, in my view, is to get these errors to be as small as possible to break the model, actually. So any deviation from the model will tell us there's this missing physics once we clean up all the systematics. And if we have missing physics, the physics is probably very important, because you notice that a lot of the manifestation of the phenomena that we had to fix by adding components are related to gravitational effects. So it may have to do with the gravity sector, which would be super interesting. Could also be other particles. That's to me the motivation behind getting smaller error. Now you can ask, but do you need 10 times better, 100 times better? And that's actually a difficult question, because for that you need sort of theoretical. You need the theorists to tell you at that scale you'll see something new. They're very creative. They tell us all sorts of things, but there are many scales at which, to me, on the observational point of view, we extract as much information from the universe we have available in our sky and hopefully break the model. If we break it, it's great. If we don't, then we run out of information. Then we don't know what dark matter is. Yeah.
At some point you said that you're using TMD results to then project them into the small, like a nearby universe.
Yeah.
So why not artificially fixing that so that they match? Does it break something else? Or?
Artificially, yeah. Well, I mean, you can artificially do that, but then you won't fit the CMB data anymore, right? So it's really the amplitude. So this tension, again, slightly simplified, is a difference between the amplitude we see at redshift 1100 and the amplitude we see at redshift 1. So of course, if you force the CMB, the model to agree at redshift 1, then it won't fit at redshift 1100 anymore. Now you can try to add new physics to try to fit both, or try to fix some systematics. Yeah, but you can't. That's the point. There's a tension. They're not within the lambda CDM model. There's a small to sigma incompatibility between these two data sets. Yeah. Mm-hmm.
So what's the outcome of these probes are low start to then go back?
Yeah, very good. So we did a lot of work on this also on the information content. So it's still so the data set that we are using now for this analysis is the Planck primordial fluctuation map, the Planck lensing map, the KIDS survey, and then the BOSS surveys. This is a forecast. We're not we haven't done we're measuring measurement now, but this is a forecast. But this is modeling these experiments, and with that combination, which is sort of one of the latest CMB information and not the latest large-scale structure information, but all public data, then it's still the CMB that dominates completely. Okay, but in the in the dark energy sector, these large-scale structure measurements are more powerful because the dark energy is important at low redshift, and they give much stronger constraints. So here it's still the CMB, but you still get a lot of information in the cross correlation between the CMB and the other probes. In the future, when we have the full stage 3s and even more the stage 4, then it'll be, as I said, comparable. If you do a Fisher matrix forecast or even MCMC forecast of the stage 4, they become even more comparable to the CMB. So then it'll shift. The great thing about this multi-probe analysis at field level is that we can add, we marginalize over systematic parameters, let's say an amplitude, for example, of calibration amplitude. Now, if you do one probe by probe, you're going to fit it and have a value of this calibration parameter. If you do another probe, you'll get another value for its calibration parameter, and they might be incompatible. But if you do everything simultaneously and you sort of auto-calibrate the systematic parameters, then you might, by just shifting a little bit one, you might fix the tension, actually. And this is what we saw in an earlier result. You don't need to change too much the calibration and no longer have the tension. It's just that if you do the analysis separately, they look incompatible, but actually they're not. And that's where the information content can also be looked at, also including the cosmological, the systematic parameter. Yeah, sure. It's also sensitive. I mean, Aurel can tell you more about it. It's also sensitive. So we use Aurel's barrier unification correction with the displacing the particles to test whether the measurement is robust to it, and then we stop on scales where it makes too much of a difference, basically. Yeah. So it's what you are saying, right? We extract more information, so now we have to test these models, beyond the 2-point function. Here, with the nice thing is that with Aurel's model, we have a realization of this baryon correction not only at the 2-point function but at field level. Yeah, and then we test with various. We can marginalize over the uncertainty on the baryon parameters and then be conservative in that cut. That's why our constraint, even with our 2-point function, are not as strong as the official 2-point function analysis, which goes further because they think they can use smaller scales because at the 2-point function, they believe the baryon correction better. This one. This one.
Where the field is what we're doing now in EV class, comparing pixel by pixel. I'm just wondering where does machine learning enter here? Because in principle, if we have something that compares pixel to pixel, that's all pixels.
That's another way. So if you can have, so if you can do inference without going through the compression of a summary statistic, which I know I think you're working on some, then that's another way. So you can do directly pixel to constraints. That's another, that would be another route. So the motivation is the fact that we have this unsolved problem of capturing the non-Gaussian information, right? And we try with various summary statistics, and the hope is that the machine learning can capture eventually more than the humans. And we can discuss whether we'll believe it or not, but that the machine learning will be capable of capturing more non-Gaussian information, especially when the data becomes more and more complex. So because of course the motivation is eventually we'll add many, many probes, so many, many maps. Can we still at pixel level or with summary statistics be able to, the complexity will be such that I think at some point it'll become very difficult to do. And the hope is that the machine learning can still find very weak correlations between that map and still improve on the constraints. That's the motivation. I mean, that's one motivation. Another motivation, of course, is that it's technically fascinating to see whether these deep convolutional neural networks, which were designed to separate cats from dogs, can do this. And the fact that they can, this is a very general machine learning algorithms. The fact that they can do so well is amazing, but that's more like a technical. It's definitely, to me, it's very interesting motivation, but that's a technical motivation or it's computer science motivation, maybe. Yeah.
Take it out.
The simulation is the instrumental artifact. So like if you are doing some kind of a CNN or DNN in this case, you have some 0 to 1 scale, and one will mean that machine learning picked up this particular. So the instrumental artifact is probably included.
Oh yeah, I mean that's critical. So you need to include all the instrumental artifacts. Yes, so we can, or sometimes we marginalize over instrument. Our instrument, we have an instrument model. So we have a sky model, which is like the weak lensing map. Then we have an instrument model, which would be like a DS imaging, simulation. And if we have uncertainties on the instrument model, then we marginalize over that. Typically, the calibration of the instrument model is typically quite good. So that's not the dominant, but we in principle can. Yeah. So, but it has absolutely to be put in, because otherwise, the machine is going to pick up instrument artifacts and think it's cosmology. Yeah, that's critical. That's one of the major difficulty. But if you do the classical one, where you do the 2-point function, you also have to model and inverse, correct all these instrumental artifacts at the 2-point function also, right? So here you just quote unquote forward model it. You don't have to correct for it. That's the advantage. Yeah. Okay. Yeah. Good level.
Yeah.
Yeah. Okay. Okay. Well, I thought.